I am going in with the thinking that you do not have zero knowledge, that you have some knowledge. Okay, because by right you should have tried to be of the SMS. So let us go in to homeostasis. Last week, did I start on this? We did. He said we played the game. Right, then two people came up to my table to play, right? What was it? Oh, Kyra, you came out to play, right, on my computer? Okay. Hey, you all need to help me, are you talking to the wall there, y'all? Okay, so I'm going to start this. So we've done one. Hey, this year, are you all out to win the CNY competition? Okay, competition. Because last year, no matter how hard we tried, it was quite clear you're all going to win. So, are you all trying this year? Because if you're not, right, we are going to try very hard. But if you are going to try, right, I'm going to tell my class just give up. So, are you all trying? Who's the class chair? You're the new class chair? Okay, so are you all trying? How many class here? I'm going to tell my class to go all out already, yeah? Okay, ready for today? May I ask anyone absent today? Okay, absent or not? Still the same, I'm still recording. You still go to Lumos, the website, you will see updated there. Okay, you will see our class videos updated there. Okay, first and foremost, to start off today, I'd like to recap this game that many of your friends played last week. This game is really a game of regulating many conditions in your body. If you look at this particular game, there are many conditions here. From how fast your heart rate is, to how fast you breathe, to your blood pressure, to how much you sweat, to how much sugar is in your blood. There are actually many more conditions in your body that needs to be regulated within a nice narrow range of values. What is this nice narrow range of values? It differs for each condition, but there are specific ranges. In this game, when you started off this game, you find that this person's condition starts to flicker. The ideal range is within this middle ground, but it could fluctuate, become too high or too low. And if I leave it for long enough, the person could die. Here, this person's temperature is increasing really high, but the body is not quite doing anything to counteract this. If I wanted to save this person, what I could do was to get this person to perspire more. And when this person perspires more, temperature starts to go down. Currently, the sugar level is a bit too low. I could try to save this person, right? And now everything's out of whack, and the person is dead. You look really devastated. This person is dead, and as you were playing this game last week, perhaps one thing you found was that it's not very easy to keep everything in the narrow range that is normal and good for you. In fact, can you imagine if I give you 12, 20 more conditions to manage at one go? That's why I think the beauty of homeostasis, which is this chapter, is that your body is unconsciously doing all this at any one point in time. You are always, at any one point in time, always trying to maintain balance. If you try to do it consciously, you cannot focus on my lessons, right? So, what's the point of this particular chapter? The point of this particular chapter, we're going to investigate how our body is able to strike and maintain this balance of all the conditions. Yes? That was fast. Okay, there's a nearby tree. Quickly, are you okay? Yeah. Okay, so I'm going to perhaps skip this, or did we do this last week? Oh, we did, okay. Then we're going to go to number 2. Many of us agree that once we're out of this normal range, bad things will happen. We will start to feel the symptoms of our body feeling a bit off. You won't die immediately, but you may die somewhere down the road, right? If the condition is out of the range for too long. Today, let's start out first with the principles of homeostasis. This particular diagram I provided over here is also found in your textbook. I'd like to remind all of you, for those that were not here last week, how the SLS this year is organized in relation to your textbook. Okay, those that were OGLs, thank you for your service to the National Junior College. If you look at how this is organized, you'll find that every page matches a section of the textbook. Okay, it's deliberately done so based on your feedback from last year. And sometimes you don't know what, when we're doing something in class, you don't know how it matches to your textbook. So we match it very deliberately for you this year. You look at tab number 1.2, the need for homeostasis. You don't really need to go to your textbook now. You will find the same section, number 1.2. Okay, that's 1.2. The need for homeostasis. Right? Today we're going to go on to 1.3, which is tab number 2. And if you search in your textbook, you will find the same section, 1.3. Why did we design it this way? So that now you know exactly where you can take down notes from. Okay? We hope that this additional layer helps you a bit. For those that are not here last week also, I want to let you know now, you will not get any more TEs. Okay? With the mid-year exams gone, we now have a little bit more time. We squeeze the TEs as much as possible within lesson time, where it is most relevant. Right? I remember some of you give a feedback and say that actually after we complete the whole chapter, we start doing the TE, we don't know how everything relates to each other. So now we have cut up the TE and park it immediately after you learn the concept. Where can you find these TE questions? You go to the SLS, you'll find that every time after a particular section, the next section will be this thing called practice makes progress. This is where we have top the TE questions that are most relevant to what you have learned. For students that find that I'm a bit too slow and you already understand what's happening, actually what can you do? Go and practice first. Okay? Practice first, and eventually when it comes to time, I'll go through it with all of you. Okay? So this is the learning cycle we want to take this year. Last but not least, at the end of each practice makes progress, I will have an exit pass, and then you all give me a sense of how you feel about the lesson. Whether you understand, don't understand. And you can include extra questions that you have for me, which I will address during or the next lesson. Because I know some of you, most of you, a lot of you here are very quiet. But I know your brain is active. If you have questions, just put it here and I will address to you. Okay? So I hope it's more complete this year and you feel like you know where you are. Let's begin with number 2 today. Principles of homeostasis. You can refer to section 1.3 of the textbook, or you can stick to the slide, to the SLS, where we will do some activities or get your input. First and foremost, today, very important to understand this cycle. Okay? For your body to be able to regulate any condition, it needs largely 1, receptor, 2, control center, last but not least, an effector to be able to regulate this condition. For those of you who have done your SLS, the first part that is required is a receptor, sometimes also known as a sensor. What is this receptor or sensor's role? Its role is really just to detect whatever change in the condition is. So change in condition. And this condition could be all of the conditions we're talking about. But today, we may just focus on one temperature. Okay, but a lot of conditions could change. Your internal body temperature, your amount of sugar in your blood. Other things could change. Maybe your blood pressure could change. Lots of things could change. But for your body to respond to the change, you must know that there's a change, right? So that's why we need a receptor or a sensor to sense, to receive information that things have changed. example of a receptor or sensor. Well, if your body temperature changes, right? In order for your body to know that temperature has changed, it needs to have something to detect change, right? Okay, so actually our body has receptors called thermoreceptors. Okay, very, very easy name, right? Thermo means temperature, receptors means to detect. So our body has thermoreceptors to detect change in temperature. If we want to detect the amount of sugar in the blood, then we will need things like sugar receptors. Yeah? So, for every condition, there is a receptor that can detect change. But today I focus on just temperature. You're writing a lot. I don't know why you're writing. You just say a lot. Okay. After your body has detected the change, it needs to respond to the change, right? If your temperature is too high, I need to bring back down. It's too low, I need to bring back up. Before I can respond to the change, I need something to coordinate this change. Meaning of, I need to send information into this place called control center, which will then send signals to regulate whatever parts of the body that will execute the change. As the name suggests, control center, it really controls what will happen next. Okay. Last but not least, when the control center has received the information that change has happened, its next step will be to send information to something called effectors. To bring the temperature back to normal. So what effectors do, if I summarize, right, their point is to counter the change. And you see that actually this is a very elegant system. It's not very complicated. I just need something to detect the change, which will relay the information to the control center. Then the control center will just send a signal to an effector that will counter the change. It's a very elegant system. We call this system a negative feedback system. Because whatever just happened, the system acts to counter it. So it's negative. Temperature is high, I counter it by bringing the temperature down. That's why I say it's a negative feedback system. If the temperature is low, I counter it by bringing the temperature up. And you use the word negative because it counteracts whatever the original change was. One common question that's asked is, will this counteract of change continue on and on? It won't. It makes sense eventually for it to stop. How does it stop? Well, remember that the receptors don't go away. They are still monitoring the condition, right? So if we brought temperature back down to normal levels, the receptor will detect that it's now back to normal, send a signal to control center. Control center will send a signal back to the effector to tell them, hey, job is done. We can reduce our work. Yes?
How to answer the structure for the count?
Say again?
If they ask you how does that process stop, how do you answer in words?
Oh, okay. So if someone asks, how will you put this into words? You could say that when the temperature or whatever condition has returned back to normal, or actually, now that you mention it, we actually do not need to describe it. Usually the last sentence goes something along the lines of that eventually the condition returns back to its normal range. Full stop, end of story. Yeah. So I noticed that actually we never quite asked of you to describe how this eventually stops. I'm just sharing a little bit more. Because one question students often ask is, does this continue on and on? Okay? Does it make sense? I put you in the hot sun, then after that your body temperature goes back to normal and starts to dip down to sub-zero. Does it make sense, right? So it needs to regulate itself and learn when to stop. Yes?
But like, you say like, the put command in like the sun, but then like, only need to be constantly keeping to maintain the level.
Yes?
So it doesn't stop.
Yeah, okay. So, okay, how you want to say is, if I put someone in the sun and he does not get out of the sun, actually his temperature will start to rise, right? The body will constantly try to fight it and counteract the change. So the body is constantly counteracting the change. Unless how young you step back into the shade, then after that you can stop that counteracting. I introduced the word negative feedback because there's an opposite of this. There's something called a positive feedback system. Positive feedback system. A positive feedback system, I do not need you to go in depth into it, but I just want you to know that this exists. And it's very funny. It is not something that is used in homeostasis. And you'll see why. A positive feedback system, I say again, it's not used in homeostasis. But our body does use a positive feedback system sometimes. Okay, give an example. Childbirth. When baby is starting to come out of the birth canal, baby will exert pressure on the mom's birth canal. Right? Send signals to control center will send signals to the effector to tell the effector to open up the birth canal a bit more. Okay? As baby exerts more pressure, what this positive feedback system will do is that the birth canal will open more and more and more. A positive feedback system is something that the effect will increase more and more and more. This is something that I do not need you to go in depth with because we do not use it in homeostasis. It will be weird if as the baby is coming out, exerting pressure on the birth canal, then the birth canal tries to counteract it and starts to and shrinks. The baby cannot come out. So a negative feedback system kind of counteracts whatever the condition change was. And this is really just the foundation of homeostasis. Very rarely will I test you this model by itself. You will start to see this model applied across our topics for this year. And I'm going to give you an example now. The skill to pick up for you to know if you understand this is simply this. Let's go up to the top, the success criteria. You are able to identify the stimulus, receptor, effector, and corrective mechanism in negative feedback. Okay? What I'm saying here is that if I provide you a context, can you roughly tell me who is the receptor here? Who is the control center? Who is the effector? And what, when I say corrective mechanism, I mean what is the effector doing to bring about the change? I'll give you an example now, and we can try together. Then you see whether you understand these concepts and know how to identify. Because that is the real skill here. Not so much to memorize these three out of context. So let's watch this video down below. And you will have done this in your SLS before, if you did your holiday homework. But let's recap this video. As we watch this video, you can already start to fill in the blanks and share with the class what you think. Okay? Here in this interactive thinking tool, stimulus, receptor, effector, I just want you to identify which you think are these three. And you tell me if you think it's a negative or positive feedback loop. As we watch the video, you can begin to key in. And as your friends key in, you can click view all to view your friends' work. And then we learn along the way together. Okay? So let's give this video a watch.
Imagine you're lost at sea and really dehydrated. Water levels in the blood decreases, and this makes the blood more concentrated in solids. In other words, the osmolarity of your blood increases. This is detected by receptors in the hypothalamus. These receptors are called osmoreceptors. When the osmoreceptors detect an increase in blood osmolarity, it sends more nerve signals to the pituitary gland. This results in more antidiuretic hormone to be secreted into the blood. The secreted antidiuretic hormone then travels to the kidneys where the nephrons are. Nephrons in the kidney filter waste products, salts, and water out of the blood. The last part of the nephron, called the collecting duct, is where water reabsorption is regulated. Antidiuretic hormone receptors are located on the walls of the collecting duct. When antidiuretic hormone binds to the receptors, it causes a cascade of reactions in the cells. Vesicles containing aquaporins, which are membrane protein channels that allow osmosis to occur, will be inserted into the walls of the collecting duct. More water can now be reabsorbed from the filtrate into the blood at the collecting duct. And as a result, the filtrate and eventually the urine becomes more concentrated and lesser in volume. In addition, because there is now more water in your bloodstream, the blood osmolarity decreases back to its normal range.
So Finia asked, right, where do we stop when we describe? Finia, as you can see here, we stop when things return back to normal. Okay? That was my voice, you cannot tell. This is a brand new context that you've never learned before. Okay? But even though it's brand new, could you identify the stimulus, the receptor, the effector? Okay, let's try now. If this video was too fast, feel free to replay certain scenes so that you can try to identify. That's the real skill here. If you can identify even though you do not know, and this context and it's brand new, that means you know how to do it. if you see the word stimulus, it means the change in condition. Okay? That's what it's trying to ask. The word blood osmolarity is very new to all of you. I put it in simple terms, it just means salt concentration of the blood. Okay? In simple terms. If you are done, have a look at your friends' responses. See what they think. Personally, even now as a teacher, I find it challenging identifying the effector. Like, which one is the effector? Okay, about a minute more, we're going to review both tests, whether you think it's negative or positive also. time I try to find your name in the class list, right, I get lost. I keep forgetting that it's your name. Alright, let's review your friends' responses. Get a diversity of thoughts. You can also scroll through there to look at your friends' work. Okay, largely, let's look at the stimulus. What is the stimulus here that's being detected? I see at least the first row, Kyra, Season, Hao Yang, all talked about blood osmolarity. That's what it was detecting. And they were very specific about it. It detected an increase. Okay? I like that they made it very specific. They didn't just say that the stimulus is blood osmolarity. Blood osmolarity is always there. Or what is the stimulus is the increase of the blood osmolarity. Let's look across the board other stimuli. Zhiwei phrased it a bit differently. He said high blood osmolarity. It's also fine. It implies a change of some sort. Henry says blood is very concentrated. Actually, I like that way of saying it is an easier way to understand for someone that don't understand what blood osmolarity means. Yeah, it is very concentrated. Okay, and I think largely I see most of us need to include some sort of a descriptor in front of blood osmolarity to give a sense that there was a change. Let's now look at the receptor. What is the receptor in this case that detects the change? I like that usually the receptor, right, is quite obvious because in its name it comes with receptor. Yeah? So as we scroll through our responses, many of us identified osmoreceptors as the one that detects the change. Shafika was very good. She said osmoreceptor in the hypothalamus. She chose the location even, right? Very specific about it. Where's the hypothalamus? Is at the center of the brain. Okay. Osmoreceptors. Okay, I just want to make just a spelling kind of thing to take note of. Osmoreceptors is connected. Okay, so just take note of that. Okay, osmoreceptors. I just want to see if there's anything different. Okay, this one, just be careful. Rather than osmo, it's osmoreceptors. Okay, osmoreceptors. Now the last one is interesting. Which is the effector here? What in this system is bringing about the change, counteracting the change? Okay, and this is where I usually find a variety of answers. For example, Kyra says the collecting duct of the kidneys, because that's where more water or less water is reabsorbed. Season also agrees, collecting duct. Hao Yang says the pituitary gland. The pituitary gland was the one that produced a hormone, correct? So technically, it is also bringing about the change, right? Because without the hormone now, technically, your collecting duct wouldn't absorb more water. Okay, so this is a conundrum. Which one is the effector? Okay, let's look at the other people. Collecting duct in the nephron. So it says kidney. He zoomed out a bit more and he said the kidney is the effector. But actually, where are the collecting ducts? It's in the kidney, right? Okay, so it's still accurate. Is he wrong? We will come to that in a while. Henry says nephrons. Nephrons also is a correct name to describe what's in the kidneys. Collecting duct is just part of a nephron. Okay, so let's have a look at other responses. Jeanette says pituitary gland also like Hao Yang. So largely, we scan across the board, we see a variety. People either say the collecting duct, nephron, or the kidneys, or the pituitary gland. So, which is the one? Okay, this one is an interesting one. Antidiuretic hormone. Because without the hormone, actually, you cannot trigger a change. So now we have three possibilities. The hormone, the kidney, and the things inside the nephron, or the pituitary gland. Okay. So, the easiest way, and I'd say the best way for you to identify at least what is agreed upon largely, the one, what we consider the effector is the final one. Okay, make it easier for you, right? Some sources online will say that actually the intermediate ones are also considered considered effectors because they bring about the change, right? But at least from what we observe, in a lot of systems, when they consider something the effector, they look at the final effector. The one that really is the one that executes the change. Yeah? I understand your point of view. The pituitary gland produces a hormone, right? Without the hormone, there is no change. Right? So I would say it's easier for all of us to align. We look at the final step. Okay? Easier? Yeah? So you look at what is the final one, and in this case, the final one is the collecting duct, which is a part of the nephron, which can be found in the kidneys. And so if students say just kidneys, I would say at this juncture is still correct. Yeah? Because it contains the collecting duct. A few more chapters down the road, when we have the lesson, when we start dissecting kidneys up, I will expect you to go microscopic and describe the collecting duct as the effector. Alright? But for our level now, if you say kidneys, it's also fine. So, where does the hormone come in then? Right? Who said it? Okay. You said antidiuretic hormone. Where does this fit into this picture, this system? The hormone comes in here. Am I right? This is where the hormone is, right? It is a signal. Why am I bringing this up? Because if you notice, the receptor, the control center, the effector, they may not be located near each other. That means they need to have a means of communicating from one to the other. How do they communicate information from one to the other? It could be using hormones, or it could be using nerve impulses. Nerve impulses. Nerve impulses are electrical impulses. And if we watch the video earlier, we can see that happening actually. It's just at the beginning, you'll see a little bit.
This is detected by receptors in the hypothalamus. These receptors are called osmoreceptors. When the osmoreceptors detect an increase in blood osmolarity, it sends more nerve signals to the pituitary gland.
Okay, you see? To communicate information from one to the other, I can use two means. I can either use nerve impulses, which in this case is what we see,
This results in more antidiuretic hormone to be secreted.
and then after that, I need to communicate information to the next location.
Antidiuretic hormone
In this scenario,
travels
it is
to the
using
kidneys
hormones
and then comes out.
to reach the kidneys. So just this final layer of information. When you look at this homeostasis cycle, one thing is not elaborated on, which are these arrows. These arrows are means of communication, and it could either be making use of hormones, or it could be making use of nerve impulses. Although I put nerve impulse here, hormones here, I'm not saying that here must always be nerve impulse and here must always be hormone. It is an either or, depending on what condition it is, depending on what condition it is. Okay? Which is why the next two chapters after this, we are going to learn about the system that produces hormones. That's chapter 2 of this year. Chapter 3 of this year is our nervous system, which are all about nerve impulses. So the next two chapters, we are really focusing on arrows. How do we ensure that we can communicate information from one place to another? Yes, Hoyoung. ADH inside the video, it was antidiuretic hormone. Now, I don't need you to know this now. Okay? The key here is that it is a hormone. Yes? Yes, sir? Okay, a question has arisen. I did not ask you to identify the control center, correct? Which do you think is the control center in this system? What do you all think? Hypothalamus? Or is it the pituitary gland? Hard to say, right? Okay. When we watch this video, what's your gut feel? What do you feel? Okay, we see again,
The receptors in the hypothalamus. These receptors are called osmoreceptors. When the osmoreceptors detect increased blood osmolarity, it sends more nerve signals to the pituitary gland. This results in more antidiuretic hormone to be secreted into the blood. The secreted antidiuretic hormone then travels to the kidneys where the nephrones are.
So who's the control center here? Who says pituitary gland? Who says hypothalamus?
But isn't the pituitary gland inside the hypothalamus?
Okay, so that's why I did not ask you to identify the control center, because even if I go online and search for sources, right, people are not quite agreeable with which is the control center. Okay, so what does this mean for you? You are thinking to yourself, ayo, shucks, does that mean it's possible for me to get case studies where it's not that easy to identify these things? It is possible. Okay, but perhaps what I would therefore like to say is, this is a model that, generally speaking, you could apply to most homeostasis systems. But some systems, right, the line between who is the control center, who's the receptor, or the effector would not be so clear. I chose this case study because some of the parts are very clear, some are not. But the interesting thing is, because scientists don't quite know or cannot decide whether it's the pituitary or hypothalamus, you know what they say? They say the brain. They just say the brain.
Very inside the hypothalamus.
Yeah, because hypothalamus is very in the brain. Pituitary gland, very in the brain. I noticed that they just say brain. See a shortcut. Okay, then shortcuts is always the brain. Interestingly enough, once we start learning about other homeostatic systems, you'll find that the control center, a lot of times, is the brain. Okay? Wherever your receptors may be, let's say it's thermoreceptors on your skin, it is routed to your brain to process, then after that send information out to counter the change. A lot of the conditions, the control center is in the brain. Yes?
Isn't the pituitary gland and the hypothalamus like together?
Yeah, that's another thing. They are connected together. So, who is the control center here? That's why it's hard to say. Yeah, so no need to define it in this particular case. Yeah. But therefore, a lot of people just say brain. I would like to say that a lot of the homeostatic systems we will show you, if we want you to identify, we try to find those that are quite clear cut. Okay? But the reason why I'm telling you it's not clear cut is because once you start looking online, you'll find that sometimes it's not so hard to differentiate one from the other. Sometimes all roll in one. The organ may itself be the receptor, the control center itself, and it may own self go and effect the change. Okay? But we will try to provide you something that is a little bit more clear cut. Where it's not clear cut, you apply your logic. And your logic will usually be quite close. For example, your pituitary hypothalamus actually is brain. Okay. Now we pause a while, take a short break, we pick up some notes if you need to, and tell a story. How is this relevant to you as an individual? If almost every homeostatic condition, from regulating temperature to blood pressure to blood sugar levels, so many of the control centers lie within the brain, then your brain needs to rest. That's why you don't get enough sleep. you will feel your body is a little bit off. Because you don't get enough sleep, the main control center that's going to bring about changes cannot work. That's why you will find that when you don't sleep enough, you feel a bit groggy, you feel like you cannot quite respond to a lot of things because internally your body is struggling to maintain within that green zone. It's flickering out of it a lot. Yeah? So sleep is very important. Your control center is a control center for many things. I have a friend, I don't know if Alpha you saw this friend. I invited my friend before into a JC in a wheelchair. Were you there at that age? Okay, so I have a friend in a wheelchair. He because he got into an injury when he was at Sentosa one day, he jumped into the sea, and just because of the wrong angle of diving in, he snapped his neck somewhere over here, right? And so all the nerves from here down the spinal cord, the information no longer is going back to the brain. So he lost control. Now he can only move his bicep muscles up. Anything below that, he cannot control anymore. Because the nerve signals here no longer reach back. No, or at least anything below that was severed off cannot send signals to the brain. What are the implications of this? Okay, other than the fact that he is now paralyzed from here down, it also means that technically what has happened is that these signals are also affected. Yeah, these signals over here are also affected. And so that means we actually noticed, because I stayed with him for around 1 year plus, we were roommates. And we noticed something, that he doesn't quite perspire even if it's very hot. Think about that. Actually, why do we perspire? We perspire because we are responding to high temperature in our body. Right? And that's the way our body responds to the change in the temperature inside us. But because the rest of his body is not quite detecting a change in temperature, maybe it is, but the signals is not going to where it is needed, which is where? The control center. Because somewhere along the way over here at the spinal cord, the signals are not going back. And if the control center is not getting a signal that there's a change, you will not get the sweat glands to sweat more. And so he just told me that he realizes he doesn't really sweat, right? And when I started teaching homeostasis, then it made a little bit more sense to me why he doesn't quite sweat. So bear in mind that for this system to work, the arrows are important too. And that's what the next 2 chapters are for. We are learning about the arrows and how you can protect those arrows. Okay? Okay, now let's practice a bit. These questions are meant to be difficult. It's beginner. Take a short while to try these questions. 2 MCQ. Sorry, 1 MCQ and 2 short questions. Okay, I'll give you some time to attend these questions in class. Then we'll run through them together. Raise hand, yes. He needs to what? Yeah. Sorry, what is your question? It's hormones, is it? Okay, I mean I'm not a doctor, so I don't know really what's happening in the body. But he does not have control of when he's going to pee or not. Yeah, he has no control. So actually for him, because he has no control anymore, there is a tube that is directly inserted into his bladder. So there's a permanent wound where the tube goes in for urine coming out. That is usually a practice that's done for people who cannot urinate themselves. Yes? Yes. Okay, I think perhaps the issue here is I am not talking about temperature. Okay? If I want to elaborate, the because one is just a part of the other. Our collecting duct is just the last part of the nephron, and the nephron is part of the kidney. So technically, we say the kidney is the effector. It's not wrong because the kidney contains a lot of nephrons, which contains a lot of collecting duct. Should we ask a question? You know the example of osmolar regularity, the kidneys, right? You need to know in that now. Don't need. Okay, I will not text you this up. But a few more chapters down the road, once we start learning to dissect kidney, you will see this again. That's when I expect you to know. I simply use it today as a fresh context for you to apply. But you'll get a feedback for answer, right? example you give is an example of quality, right? Not exactly, because that is what we are teaching you about all the conditions that are being regulated, right? It is always to counteract and then keep it within a narrow range. Right. The reason why I point out quality feedback is so that when you are describing the homeostasis, actually the counteracting right is always negative. And you're right, not your best is for the method, but it is not what we are learning when you see that cycle. Yeah. I used to think that cycle, right, you can also just block and you can bring things back to normal. But not quite the case. So when you see a cycle, right, what they're trying to show you is negative feedback because you're bringing it to normal and shorter. Actually, blood clotting as an example, right? I also think because in blood clotting, right, you are using blood. What the system is trying to do is to stop you from blood clotting. Kind of, yeah. It's like you are bleeding, that means you have to stop it. Yeah, right? Yeah. But whatever we are studying, it's always a internal condition that you want to restore back to normal. Yeah. So even like childbirth, right? Also, there's no condition here we're trying to regulate. It's just not yet to be. Thank you. Yes. Yeah, please. I will first go through MCQ first, while you're still doing the rest. But MCQ is quite doable. In fact, if you can do the MCQ, the next question should be able to do also. Yeah? So the MCQ that you see over here is often used to see if you understand what homeostasis is. Is clearly the definition of it. Does it match any of the things we require you to know? I want to show you the answer. If you go to section A, one of the learning outcomes that you need to know is to be able to define homeostasis. Okay? So I would like to remind you, if you ever feel like there's too much biology to learn, you just zoom in on what you need to know over here, then it narrows things down. Do you know where to find all the learning outcomes in your textbook? It will always be found on the first page of each chapter. Okay? Each chapter will show you the learning outcomes you need to know for that chapter. And if you scroll down, you will see the learning outcomes appear again when it is relevant to the section. But the first page will provide you an overview of all the learning outcomes you need to know. So actually for this chapter, you just need to know 4 of these things. Number 1, you'll be able to define it. Number 2, you can explain the principles of homeostasis, which are the steps of it. Perhaps in a structured question or an essay. C, that you can recognize negative feedback as a mechanism that counteracts. So for example, whether you can recognize if it's positive or negative. Last but not least, outline how body temperature is regulated. You can do this for this chapter is done. Okay? So let's look at the first question. First question, which learning outcome am I trying to assess your understanding of? First question. It is kind of A, right? I'm just trying to ask you what in the world is homeostasis. So, what is the answer for this one? What did most of you all choose? Okay. The answer here is 1. Okay. I would like to tell you how we like to trick you. We like to trick you just by removing the word near. Okay? You just take out the word near, and this definition is incorrect. I'll tell you why. Because if this is a graph of your level of the condition in your body, over time, homeostasis is not trying to do this. Homeostasis is not trying to keep things at a constant. That is impossible to achieve. Even for body temperature, right now under the fan, the temperature is constantly changing because of the cold fan. You step outside, the temperature changes already. It's impossible to be a constant. But you know what our body is trying to do? It is trying to keep it within a narrow range that is still considered normal. So what you will see often in a graph is that instead of a straight line like that, you'll find that the condition fluctuates up and down within this normal range. Yeah? That is what homeostasis is. It is a near constant, but within a narrow range. Every turn you see over here, temperature go up, then turn down, temperature go down, turn back up. That is negative feedback at work. It is trying to counteract the change. And so negative feedback homeostasis prevents you from exceeding this normal range. Once you exceed, you start to feel off. The best way to feel off is you just don't sleep. Then your control center will struggle to keep it within this range. Okay, you don't nod your head because that is now, then you can, now you think, I'm going to try that. Don't need to try one. Yeah? You won't feel good. Okay. And therefore, question 2 should be quite doable. Explain what is meant by homeostasis. I'm actually asking you to define it. This is the suggested answer. Refer to the maintenance of nearly constant conditions in an internal environment. Let's look at some of our friends' suggested answers. A state of balance maintained by the body for the body to function properly. I can get the idea that the answer here is trying to say balance. Okay? But I think it doesn't quite encapsulate the idea of a near constant range. When you say balance, sometimes the first thing that comes to my mind is like you're trying to balance something like that. But that's not what we're trying to do. We're trying to keep it in a range by counteracting the change. Okay? Other ways of answering: maintenance of body conditions. Okay, I like that they mentioned conditions, body conditions, and a near constant range. Okay? If I want to change this ever so slightly to a near constant range, perhaps within a near constant range, okay, what I'm trying to do is maintain within a near a constant range, a near constant range. Now let's merge some of your answers together. There are many body conditions. No, there are many conditions of the body. But homeostasis is trying to keep the internal conditions a constant. Okay? So if you look at the proposed answer, we did use the word internal. It is about the inside, within a narrow range, near constant. Okay? Oh, this person even elaborated to give examples of such conditions. That is very nice to elaborate on. Give examples. Okay, so largely, as I look at the answers, we are almost there. Hey, this person, pay attention to my lesson. Homeo means sameness, stasis means stationary. Okay, don't define it this way because often when I talk, I'm just trying to make it more understandable. Okay, so I hope that when you see my lesson, you understand that a lot of times I try to make things more understandable in speech. Okay, so that is for this question. Let's look at one more question. Have you done the next one? Why is homeostasis important to organisms? Okay, so if you give me the idea that it's important so that your bodily functions can continue happening normally, Okay, so for example, answers attempting to relate the constant environment in order for cells, tissue, organ systems to function, for biological processes to occur, can. Something along these lines can. This question is very open-ended. Okay, some students will say you will die. Okay, are you wrong? Okay, you are wrong. You are correct, but it takes a while for you to die. Okay, you can be out of this range, but you need to be out of this range for quite a long time before you die. It is not an instant. That would be very crazy, because what if I suddenly put you in an oven, your temperature suddenly exceeds for a short while, you die already. But it's not the case. It will exceed, but your body will struggle to bring it back. Okay. Some of you may even give examples of why the conditions need to be maintained. The best example I think that is relatable to us would be on enzymes. Enzymes, we learned before, have an optimal range of conditions to occur, right? From the salt, the pH to the temperature. And enzymes are part of many reactions in the body. And so that's why enzymes are a good example you're going to give as a case study of why it's needed to maintain. So look at some of your friends' responses. Maintains the best condition of the body. Okay? Elaborate. What does best mean? Okay? Best means that your organ cells can all function normally. That is as best as it can be. It is important for organisms to maintain a constant internal environment so we do not fall sick. Okay, this is interesting. We can fall sick in many ways. We can fall sick if our homeostasis is not working. We can also fall sick because of viruses, bacteria. So when you say we do not fall sick, actually I think it is a bit too general. You're not wrong, but it does encapsulate a lot of other reasons why we may fall sick. Okay, this person mentioned enzyme activities. This will be accepted. Okay, because you did try to show examples of why it's important to maintain the bodily functions. Maintain fluidity. Wow, this is also fine. Was this from a textbook? If it's not, this is quite high level. Okay, maintain fluidity of cell membrane. Because last time we talked about cell membrane also, right? Temperature can affect it. Optimal conditions for the body. This is getting somewhere. Okay, optimal conditions. Let's elaborate. What does optimal conditions mean? And then they say for the body. So for what? So they can function normally. Okay. So, this is interesting. Homeostasis is important to control how much body intakes or releases. For example, oxygen. Okay. I would say that what you are describing is the effector part. Homeostasis is not so much important to control how much you take in and out. How much you take in and out is a response to homeostasis. I am breathing in more or out more because I need to carry out homeostasis. It's not that homeostasis controls and tells me to breathe in and out more. Okay? So a variety of answers we can look through. I will stop here. Last but not least, I think this person has brought up something that is very important. Why maintain this internal condition? We have addressed so that our body inside can function normally. But there is one good advantage of this. The advantage is that now you can adapt to sudden changes in the external environment. If the outside changes, you can adapt to it. That is an advantage. It also means that actually now, as human beings, you can go anywhere in the world. You find human beings in the hottest of places in the world, the coldest of places in the world. Because as human beings, as mammals, we are able to regulate a lot of internal conditions, even if the external ones are not the best and most ideal. Yes? Okay, is homeostasis only done by mammals? No, it's done by, I think, all living things. But some living things do not have the ability to homeostatically regulate some conditions. I'll give an example. Cold-blooded animals. There's one condition that they don't quite regulate like us. Temperature. Do you know when cold-blooded animals are cold, their body won't adjust to make itself warm? You know what you need to do? You need to crawl out into the sun. If it feels too hot, the body will not regulate it to bring temperature down. It will need to go into the shade. So, all living things have homeostatic control systems, but some have more, some have less. Yeah? Birds have an interesting way of regulating temperature. They shit on themselves. Yeah? Rather than sweat, they shit on themselves. When they shit on themselves, the shit liquid evaporate, right? They feel cool. So, no, not like I feel cool like that way, but it feels cool down. Okay? So that is the last one, homeostasis. This last question. Before we end off today, let's look at some questions that you may have. Teacher has a question mark. Teacher, what am I supposed to say? Or you have no question to me? Is it a seminar? Alright. Okay, let's look at other questions. Oh, I answered Kara's questions by chance. Kara asked, how about cold-blooded animals? Do they perform homeostasis? They do. So like blood sugar level, all this kind of stuff, right? You also got regulate blood pressure. But just for temperature, they are a bit different. Why? We are still finding out the reason why. One speculation is, if you notice, a lot of cold-blooded animals, from fishes to reptiles, they all come from eggs. Right? Okay, then people are still wondering also, so why? What makes eggs so special? And then the interesting thing is that actually all life originated from the oceans, water. And in your physics, actually, I don't know if you learned yet, water, the temperature cannot change so fast. It is quite constant. So if the earlier animals that evolved from the oceans, the seas, actually perhaps there was no need to regulate your temperature that much. Because the seawater temperature is maintained quite well. But we don't quite know. A lot of theories going on there. But once we transited to land, the condition can change very quickly, temperature, right? You need to find a way to maintain a constant inside. Oh, yeah, also asked cold-blooded. Okay, just for temperature, it's not very good. Since he asked, how can we control how our brain controls our body environment? Okay, Cici, are you asking? You're saying internal body environment, right? You're not saying like I use my brain, right, to like make something move, right? Okay. Can we control homeostasis? Is that what you're asking? Right? Could you control and say sweat, then you squeeze out some sweat? Have you been able to? I haven't. So I think we can't. Okay? But there are ways to try to override homeostasis. Okay, I'll give you an example. Okay, this is not homeostasis. Let me think. Is there a way? I would say no. But you could use external means to try to modify. How? You know homeostasis got the receptor, control center, and binding effector, right? Here are the arrows, right? What if I go and mess with the arrows? How could I mess with the arrows? If after some of the arrows rely on hormones, okay, I could mess with your homeostasis if I inject hormones in you. Yeah? Right? If I want the effectors to do more or something, right? I go and inject more of the hormones, then I could mess up your homeostatic system. Right? And that's what some treatments do. Some people who are sick, they are sick because these arrows don't work anymore. And to treat the sickness, we pump in hormones. Yeah? But in a normal human being, if you try pumping hormones, right, you're going to mess with your homeostasis. Yes?
So like sweating is like because of homeostasis, then why do we sweat when we get like nervous?
Like cold sweat.
Yeah.
Do you sweat when you're nervous?
Yeah.
I'm not sure if it's a how do you say literary metaphor. Do we sweat when we are nervous? Okay, I don't know. Yeah? Your palms get sweaty. Okay, I'm not sure if this is homeostasis, it could be a reflex action, which you will learn 2 chapters down the road. Where sometimes reflex action means something happens, we will respond to the environment in a certain way. It's not the same as homeostasis. We will learn down the road. Perhaps we can come back to it back then. Okay. Well, we also has the same fields. Can we modify our brain to control the negative system more effectively? I would say the brain very hard, but we can modify the arrows. Yeah? NIL. Oh yeah, nail lah. Okay. Okay, Pinya. Okay, not yet confident in determining the effectors in the case study. Not Pinya, it's not Pinya. Okay. Not yet. Okay. So we practice more. Okay, we'll provide more case studies, then you try more. If someone cannot control our body using nerve and hormones, is it possible to turn it back to normal? If the body cannot control, the only way to return it back to normal is that we need to externally control it ourselves. There are people that cannot regulate sugar levels. They need to, every once in a while, take out a syringe with insulin, a hormone, inject it themselves. I don't know if you've seen this before, but there are some people that need to go through this. Okay. Oh, any more? Some more questions? Oh, it's an enzyme and effector. Okay. This is interesting. I think at least in our definition of what we define as effector, it tends to be not on a biomolecule kind of level. It tends to be on a part of a body kind of level. Like your muscles, or your sweat glands, or your kidneys, or your nephrons, but not really on a enzymatic level, or maybe the sugar level, or biomolecules kind of level. Okay? Why I still fall sick? I go both places. Many things to answer here. Why is you fall sick? It could be not homeostasis, but your immune system weak. Maybe your immune system not so good. Okay, okay, so that's some of the questions for today. I thank all of you. Those of you who normally don't say in class one, I thank you for voicing here. Then this way I can answer more of the questions this year. Okay? Next time around I see you, which is not tomorrow, right? Next week, I will go through the last part of homeostasis, is part B. As a homework, may I just get you to understand part 1? Okay? So that in class, we can review practice makes progress. Okay? Enough? Wait, are we behind time? Let me just check. Are we behind time?
So I have to write.
Okay, 403, we have 7.8 weeks of lessons. You want to see compared to other classes, how much you have? 405 is the most. You are second last in terms of number of weeks. Okay. So is it okay if we speed up a little? Most classes are going to, in week 4 next week, start on the endocrine system. We are one of the lucky ones, we have the full time for endocrine system. Okay? So on your part, you just help me do part 2. Okay? What do I mean by part 2 of your SLS? Can you do the practice makes progress? Complete it. In class, we go through together. Once we go through together, I teach you how to write an essay for this. Then we go on to the next chapter. Okay? Thank you so much. Can we stop the iPad? Okay, that's all for today.